For today's lesson, we will be discussing about the normal probability distribution. So we will be discussing about a normal curve as well as the z-scores and how to convert a certain data or a certain value into its corresponding z-scores. So to begin with, let's look at this graphs of the discrete probability distribution. So this is the histogram of the discrete probability distribution, wherein we have here on the horizontal axis is the value of our random variable, and on the vertical axis is we have the value of our probability for each random variable. Now, we have here number of heads for 2 coins. That's the one that we have to count, and then we have the number of heads for 5 coins and for 3 coins. Now, looking at the graphs, as you can see, they just have the same behavior, or they just have the same or similar appearance. So from here, it gradually increases until it reach its peak and then decreases. Also with this one, it gradually increases and then decreases as well. And lastly, this, so it's like that as well. So as you can see, they just have the same behavior wherein they gradually increases and then they reach the peak at the middle and then it gradually decreases towards the right side. So this graphs here, this represents now a normally distributed data. Now, when can we say that the data is normally distributed? So the distribution of data is said to be normally distributed if the scores tend to be around a central value, which is the mean, with no bias to the left and to the right. So again, our data is normally distributed if most of the scores gather around the central value, which is the mean. And the mean should be located at the center. So if the scores are closer to the mean or they tend to be around that central value, which is the mean, then we can say that it is a normally distributed data and there should be no bias to the left and to the right. So the one that I showed you a while ago is what we call as the normal curve. So the graph of a normal distribution is called a normal curve. It is characterized by a bell-shaped distribution. The middle of the normal curve is the mean. So again, this is the bell curve, this one right here. So this is our normal distribution, and then this one is the bell curve or the normal curve, and it is bell-shaped. So as you can see, we have here flat graph and then eventually goes up to the peak and then goes down. Now this peak right here is where the mean is. So as like what I've said a while ago, for normally distributed data, the scores should be or tend to gather around the mean. So that's why most of the values here can be found near the mean. So this model provides a basis for making decisions concerning properties of population. So of course, we use the normal curve or the normal distribution to write conclusions, or that will be our basis whenever we write conclusions based on the given that we have. Now, there are properties of a normal probability distribution. First, the normal probability distribution is bell-shaped. So that is the one that I showed you a while ago. Next, the curve is symmetric about its mean. So when we say it's symmetric about its mean, so let's try to draw a curve here. Something like that. And then, so the mean should be found here at the center. So here is the mean. Now, the curve must be symmetric about its mean. So that means these two sides must be equal with one another. So this side is equal with this one. So that is another property of our normal probability distribution. Third, the mean is equal to the median and is also equal to the mode. So in a normal probability distribution, the mean must be equal with the median and equal also with the mode. So when we say median, it is the central value or the middle value if the scores are arranged in order. And then mode is the most frequent data that you can see in the group of data. Next is the spread of the curve depends on the standard deviation of the distribution. So as what we know, standard deviation is the average distance of each scores from the mean. So if the standard deviation is smaller or it's smaller in value, that means the scores are closer to our mean. So it affects now the curve of our graph. So if the standard deviation is smaller, this means that the graph will be something like this. There. So it can be something like that. Meaning the scores tend to gather more to our mean, or they are closer to the mean. However, if the standard deviation is high, so when we say the standard deviation is high, that means the scores are farther from the mean. So the curve now will be something like this. There. So if the standard deviation is smaller, our curve will be a bit compressed. If the standard deviation is higher, the curve will be a bit stretched out. The tails of the curve flatten out indefinitely along the horizontal axis, always approaching the axis but never touching it. So we have here the horizontal axis, this one, and both ends of the curve, or the tails of our curve, flatten indefinitely along this axis. So it should be flattened right there. But the curve and the horizontal axis are asymptotic with one another, so that means they will not touch, but the graph or the curve will just approach the horizontal axis. And lastly, the area under the curve is equal to 1. So when we get the area of this, so this should be equal to 1. Remember, the sum of all the probabilities of a certain distribution should be equal to 1. So that's the reason why the area under this curve should be equal to 1. So now let me just show you the curve. So this is the normal curve. And as what we know from the properties, the mean is in the middle. So here's the mean. And then it divides our curve into two symmetric sides. So aside from the mean, we can also locate the standard deviations in our normal curve. So usually, we can just put up to 3 standard deviations only. So this one, okay, so this means that the points here are 1 standard deviations away from the mean. So if the point is here or the value is here, it is 1 standard deviation above the mean. If the value is here, it is 1 standard deviation away from the mean or below from the mean. And here, at this point, so this one now is 2 standard deviations above the mean. And then on this side, it's 2 standard deviations below the mean. And lastly, this is 3 standard deviations above the mean. And this one is 3 standard deviations below the mean. Now again, usually, up to 3 standard deviations only for our normal probability distribution. So the reason behind that is because of what we call as the empirical rule. Now, what is the empirical rule? So the empirical rule tells us how many percent of our data falls within the different ranges based on the standard deviations. So we have here 3. So the empirical rule states that 68.26% of the data falls within 1 standard deviation away from the mean. So if we will just go back, to our graph, this is the 1 standard deviation above and below the mean. So if we will just draw here something like that, and also on this one, so we can say that this area here, or the scores within the range of these 2 standard deviations, that already covers 68.26% of the data, or 68.3%. So if the scores are from the first standard deviation above and below the mean, then that covers already 68.3 or 68.26% of the scores already. Next is for the second one, 95.44% of the data falls within 2 standard deviations away from the mean. So it means that from the 2 standard deviations above and below the mean, so let's change this one. So from this range, 2 standard deviations above and below the mean, that already covers So this one. So this range, this already covers 95.44% of the data. So it is said that if your scores are normally distributed, 95.44% of your data must be 2 standard deviations above or below your mean only. And lastly, we have for the 3 standard deviations away, so that is 99.74% of the data already. So 99.74% of the data falls within 3 standard deviations away from the mean. So let's just go back here. Now from this range, 3 standard deviations away from the mean, this already covers the whole, this one, there. And it already covers 99.7% of the scores. So that means we're just going to consider up to 3 standard deviations for the normal probability, because that already covers 99.7% of the scores. Now, how about the remaining 0.3%? So the remaining 0.3%, so let's just draw here this one. The remaining 0.3 will now be divided between the 2 sides. So this one is 0.15%. The other one is also 0.15%. So it is possible for us to get values from our data that are above 3 standard deviations away from the mean. But it is very unlikely because that is only 0.15%. So that is what empirical rule states. Now, this is just a formula that we follow, or the function that we follow if we want to graph our normal curve. So the normal probability distribution function follows the form f of x equals 1 over the standard deviation times the square root of 2 pi times e raised to negative 1/2 times the quantity of x minus mean all over standard deviation squared. So again, this is just the formula or the function that we can use if we want to graph our normal curve. Now, let's try to draw our normal curve based on the mean and the standard deviation. So this is just a rough graph of our normal curve. But our goal here is to identify what's the location or where is our standard deviations located. So first is you have to identify the mean. So the mean is 5. So you identify where is 5. So there. So this is 5. This is where our mean is. Now, to get the first standard deviation, again, we're just going to compute up to 3 standard deviations above and below our mean. So for the first standard deviation above the mean, all you have to do is to add 0.5 to our mean. So the first standard deviation, so you add and subtract 0.5 to our mean. So we now have the values 5.5 and 4.5. So this is 5.5. So that is where our first standard deviation is. And then 4.5 is the first standard deviation below the mean. Next, for the second standard deviation above and below the mean, we now have to add and subtract 0.5 from the first standard deviation. So 5.5 plus 0.5. And we also have 4.5 minus 0.5. So we now have 6 and 4. So this is where, so 6. So in 6, that is the location of the second standard deviation. For 4, that is the location of the 2 standard deviations below the mean. And lastly, for the third standard deviation, we have to add and subtract again 0.5 to 6 and 4. So 6 plus 0.5, and we have 4 minus 0.5. So that is 6.5. So this is where our third standard deviation is, and 3.5 for the 3 standard deviations below the mean. So this is now the location of our standard deviations, and then we already have the mean. So we can now draw the graph. So this is just, again, a rough estimation of the graph. So as we go towards the 3 standard deviation, it should be closer now to the horizontal axis. So let's just try to draw this. So it's something like this. There. And also the other side. Again, it's not that accurate, but you get it already. This is now the graph of our normal curve. Again, this is just a rough estimation. What's important here is we're able to identify the location of our standard deviations. And another one, let's have this. Mean is 3.2, standard deviation is 1.2. So again, let's identify the mean. So let's say the mean is here, which is 3.2. And then for the first standard deviation, so we add 1.2 to 3.2. So for the first standard deviation, we add 1.2 to 3.2. So that is 4.4. So let's say 4.4 is here. So that is where our first standard deviation is above the mean. And then for the first standard deviation below the mean, you just have to subtract 1.2 from 3.2, and that will give us 2. So this is the first standard deviation below the mean. Now, for the second standard deviation above the mean, we just have to add 1.2 to 4.4, and that is 5.6. So this is where our second standard deviation is above the mean. And then for below the mean, so 2 minus 1.2, that will give us 0.8. So here is the second standard deviation below the mean, so 0.8. And lastly, for the third standard deviation, so we just have to add 1.2 from 5.6, and that will give us 6.8. So let's say somewhere here. So that's 6.8. So that is the third standard deviation above the mean. And then for the third standard deviation below the mean, we just have to subtract 1.2 from 0.8, and that will give us negative 0.4. So let's say it's here. So that is now the third standard deviation. So those are now the locations of our standard deviation. So we can now draw the graph or the curve. So again, it should flatten towards the third standard deviation. So something like that. Okay, and then like that. So that is now the graph of our normal curve and also the location of our standard deviations. Now we have what we call as the z-scores. Now when we say z-scores, it refers to the distance between the given value and the mean. The distance is measured according to how many standard deviations the score is away from the mean. So when we say z-scores, again, we are talking about the distance of that certain value and the mean. So we are going to convert now certain data or value into z-scores. When we say we convert a certain value to z-scores, we are converting it into distances in terms of the standard deviation. So we will check how many standard deviations away our score is from the mean. So let's just go back to our normal curve. So again, we have here the mean. And we know we have 3 standard deviations here. So let's just divide this. In getting the first standard deviation, we add the standard deviation to the mean. And we also subtract it from our mean. And to get the second standard deviation, we can just add the 2 standard deviations from the mean. And here, 3 standard deviations from the mean. On the other side, just subtract 2 standard deviations from the mean and 3 standard deviations from the mean. Okay, now when we say z-scores, again, we are computing the distance of each value from our mean. So in z-scores, the mean is already equal to 0. That means the reason why mean is 0, because again, we're talking about distance from the mean. So automatic, it will be 0. Now, for the first standard deviation above the mean, so that will be 1. Now, what does 1 mean? That means that particular value is 1 standard deviation above the mean. However, if it's negative 1, if the z-score is -1, that means the score or that particular value is one standard deviation below the mean. So as you can see in z-scores, we have negative, although we are talking about distances, but these signs will tell us if the particular value is above or below our mean. So for the 2 standard deviations away from the mean, so that is 2, and for the 3 standard deviation, that is 3. Here we have -2 and -3. So if the z-score is -3, that means it is 3 standard deviations below the mean. If the z-score is 2, that means it is 2 standard deviations above the mean. Now, of course, not all the scores will fall exactly 1 standard deviation above or below the mean, or 2 or 3. So we have to use the formula, this one, in order for us to convert certain values into z-scores. So we will be using this formula, z equals x. X refers to the value or the data that we have minus the mean all over the standard deviation. So this is the formula that we will be using if the score is within a population. And this is the formula that we're using if the score is within a sample. But for now, we will be using this only. So this formula above. Now let's try to determine the z-scores of the given set of data. So I have the mean, which is 12.5, and also the standard deviation, which is 2.5. Now we have to convert these certain values, 9.5, 16.5, and 19.2, into their corresponding z-scores. So all you have to do is to substitute it from the formula. So z equals x, 9.5, which is the data, minus the mean, which is 12.5, all over the standard deviation, which is 2.5. So same case with this one, z equals, and then you have x, which is 16.5, minus the mean, 12.5, all over 2.5. And last, we have z equals 19.2 minus the mean, all over 2.5. So next is we just have to simplify this. So 9.5 minus 12.5 divided by 2.5, that will give us -1.2. So that is now the corresponding z-score of 9.5. Next, for 16.5, so 16.5 minus 12.5 divided by 2.5, that will give us 1.6 as the value of the z-score. And lastly, for 19.2 minus 12.5 divided by 2.5, that gives us 2.68 as the z-score. 2.68 as the z-score. So there. So now we're able to convert our given value into its corresponding z-score. Now, how are we going to interpret this? So let's say the x is 9.5, or the data or the value that we have is 9.5. If its corresponding z-score is -1.2, it means that 9.5 is 1.2 standard deviations below the mean. So as you can see, it's negative. That means our score is below the mean. So how far it is from the mean? So it's 1.2 standard deviations below the mean. For the 16.5, since the z-score is 1.6, so it's 1.6 standard deviations above the mean. And then for last one, 19.2, it's 2.68, so 2.68 standard deviations above the mean. So if we will look at the values here, obviously the farthest from the mean is the 19.2, because it is 2.68 standard deviations above our mean. So that is how you solve for the z-scores, and also how to interpret the z-scores. And last, let's have this. X is 30, 11.3, and 32.1. Now the mean is 25.7, and the standard deviation is 5.1. So let's have here z equals 30 minus 25.7, or minus the mean, all over the standard deviation. Also this one, 11.3 minus 25.7 all over 5.1. And z equals 32.1 minus 25.7 all over 5.1. Now, let's solve for the corresponding z-scores. So, 30 minus 25.7 divided by 5.1, that gives us 0.84 for our z-score. So, you just have to round off to 2 decimal places. And next, 11.3 minus 25.7 divided by 5.1, that gives us negative z equals negative 2.82. And then lastly, for 32.1 minus 25.7 divided by 5.1, that gives us z-score of 1.25. There. So these are now the corresponding z-scores. So for 30, it is 0.84 standard deviation above our mean. So it's the closest score or data from our mean, because it is within the first standard deviation. And for 11.3, it is 2.82 standard deviations below our mean. And last, for 32.1, it's 1.25 standard deviations above our mean. Again, that is how you convert particular value into its corresponding z-scores. So that's it for today. I hope you learned something about the normal probability distribution as well as the z-scores, and see you next time.